All right, so the really nice thing about gases is that there's a very simple relationship between pressure, volume, and temperature of gas, and how those three properties change, how changes in those properties affect the other properties. So we're going to talk about one of the mathematical relationships between those properties, which is called Boyle's law. So Boyle's law states that the pressure and volume of a gas sample are inversely related when moles of gas and temperature are held constant. So this is what we saw in experiment 5 in the lab. We saw that P times V was equal to a constant, or that pressure was inversely related to volume. We had a syringe filled with air. We attached it to a pressure sensor, and when the plunger was depressed, when we squeezed on the syringe, we decreased the volume of air in the syringe, and we watched the pressure go up. So this is a graph that probably looks like one that you made. So this shows the inverse relationship. So as volume goes up, pressure goes down. And as pressure goes up, volume goes down. So at low pressure, the volume is large. And at high pressure, the volume is small. All right, so that's what this says here. Pressure is low. The gas sample has a large volume. Gas pressure is high. The sample has a small volume. That is when temperature and moles of gas are held constant. So the relationship between pressure and volume is an inverse relationship. Volume is, this is a proportional symbol. Volume is proportional to 1 over pressure. And if we want to make a proportionality constant, we say that pressure times volume is equal to a constant. We're going to call it K sub B because the B is for Boyle's law. Because P times V is a constant, we can calculate a new pressure or volume of a gas when 1 is changed. So what that means is that P1 V1 equals P2 V2. So that comes from the fact that we have pressure 1 and volume 1 at our first state of the system equal to K, and pressure 2 and volume 2 at our second state, the changed state of the system, is also equal to KB. So, because KB is the same, we can say that these are the same. So let's use that. We have a sample of gas with a volume of 696 milliliters at a pressure of 4.39 atmospheres. So I'm going to call that volume 1 is 696 milliliters, and pressure 1 is 4.39 atmospheres. All right, let's keep reading. The gas is compressed and now has a pressure of 8.01 atmospheres. So pressure 2 is 8.01 atmospheres. Predict if the new volume is greater or less than the initial volume and calculate the new volume. So we want to find V2. Assume that temperature is constant and no gas escaped. So temperature and moles are constant. All right, so let's think about this let's do our prediction first. So our original volume was 696 milliliters and our original pressure was 4 atmospheres. We increased the pressure to 8.01 atmospheres. So because pressure and volume are inversely related, when pressure goes up, volume goes down. So our new volume should be lower than our original volume. So let's check. So we're going to use this equation that I just showed you. P1 V1 equals P2 V2. So we're going to have 696 milliliters times 4.39 atmospheres equal to 8.01 x. So we're solving for x. So we want to divide by our 8.01 atmospheres, which will cancel out atmospheres, and we'll have milliliters left over. So x is equal to 696 times 4.39 divided by 8.01. Let's calculate that. And I got that V2, or x, is equal to 381.5 milliliters. So yes, our volume decreased when our pressure increased. All right, that's it. So now we're going to learn about a couple other laws related to gases. Charles' law states that the temperature and volume of a gas sample are directly related. So when pressure and moles of gas are constant, that means that volume and temperature, when one goes up, the other one also goes up. For example, when we heat up the air in a hot air balloon, the hot air balloon expands, and that's how you get it to rise. If you consider a gas sample in a syringe, like the one we had in experiment 5, and you attach it to a pressure sensor and a temperature, and we change the temperature by boiling some water or getting some ice, like we did in experiment 5, you can measure the volume. So what we did, we measured volume and pressure, and we measured temperature and pressure. So this law relates volume and temperature instead, but volume and temperature and pressure and temperature have the same relationship. So we're going to talk about volume for Charles' law. So temperature, when temperature goes up, volume goes up. So at low temperature, the volume is small, and at high temperature, the volume is large. So the black line is for hydrogen gas, the green line is for oxygen gas, but both have a constant slope that is increasing, showing our direct relationship. So, like we said, when pressure and moles are constant, decreasing the temperature makes the volume decrease. The two properties are directly related. What that means is that V is equal to some constant times C, and we're going to call that constant Kc, C for Charles. If we rearrange that equation, we see that volume over temperature is equal to Kc. So you should have seen this with pressure and temperature in experiment 5 instead of volume and temperature. Anyway, because volume divided by temperature in Kelvin, it has to be in Kelvin, so keep that in mind. Because volume divided by temperature is a constant, we can calculate a new volume or temperature when one of the properties is changed. So what that means is that V1 over T1 is equal to Kc, which is equal to V2 over T2. So you can make them related to each other. And this is how we're going to calculate a new volume or a new temperature from an old volume and an old temperature. And one last thing you guys can note is that this is the part that we took out of experiment 5, so you didn't have to do this. But if you extrapolate the volume versus temperature plot to the point where V equals 0, then because V equals 0 we're proportional, T also is going to equal 0, and that temperature is negative 273 degrees Celsius, or otherwise known as 0 Kelvin. So if you extrapolate back here where volume is 0 at the place where the axes meet, then temperature is a little less than 250, as you can see on this graph, and it is precisely negative 273 Celsius, or 0 Kelvin. So this is why you always have to use Kelvin when you're relating volume and temperature, because otherwise you have this additional temperature of negative 273, which throws off all of your calculations. All right, so let's use Charles' law. We have a gas sample with a volume of 2.93 liters, so I'm going to say that's volume 1, and a temperature of 55.8, so I'm going to call that T1. And note that is in degrees Celsius. Our gas sample is heated to a temperature of 122 degrees Celsius. So that's going to be our T2. We heated it up to 122 degrees Celsius. And now we want to predict whether the new volume is greater or less than the original volume and calculate the new volume. So volume 2 is our X. All right, but I told you, you have to convert to Kelvin first. So always remember that. That should always be your first step if your temperature is not given in Kelvin. So to do that, you have to add 273 to your temperature. So while we're at 55.8 degrees Celsius, we are actually at 328.8 Kelvin. And we want to convert our other one too. So we have 122 plus 273. And that is 395 Kelvin. All right, so now we have the numbers we need. So we're going to set this up as, I'm just going to use my V1 here, so 2.93 liters times the we want to do divided by T1. So divided by 328.8 Kelvin is going to be equal to our X divided by our T2, which is 395 Kelvin. So let me rewrite this a little neater. All right, so now you can see that if we want to get X by itself, we multiply both sides by our 395 Kelvin. So if we plug this into our calculators, we're going to have 2.93 divided by 328.8 times 395. So our new volume is going to be 3.52 liters. So does that make sense with our knowledge of Charles' law? We heated up our sample, so our temperature increased. So because it's directly related, the volume should also increase, and it did. Awesome. One more law for today. That law is Avogadro's law. So we talked about Avogadro a few chapters back, and the way that his name came up in the first place was that he stated that equal volumes of gas should have the same number of particles when they're at the same temperature and pressure. And this is called Avogadro's law. It states that the volume and the amount of a gas in moles are directly related when pressure and temperature are constant. So this experiment is a little different. It'd be a lot harder to do in the Gen Chem lab, but consider an experiment where the volume of a gas is measured as a function of the amount of gas in moles in that syringe at constant pressure and temperature. So as the amount of gas in moles increases, the volume increases. They are directly related. With a large amount of our nitrogen gas in the syringe, the volume is over 2 liters. When there's no gas in the syringe, the volume is 0. So there's nothing taking up the volume. All right, so let's see a little bit more about that. As the moles of gas in a syringe are increased at constant temperature and pressure, the volume also increases. So this is the same as what we saw with temperature. So volume is proportional to moles of the gas. So they are related by this constant, Ka for Avogadro. So just like temperature, V over N is equal to a constant. And just like we did with temperature, we can use Avogadro's law to calculate a new volume or number of moles when 1 is changed. So that's the same as what we saw with temperature. V1 over N1 is equal to V2 over N2. And one thing to note is that Avogadro's law is independent of the identity of the gas. So it doesn't matter what type of gas we're talking about. We can talk about nitrogen gas. We can talk about argon gas. We can talk about xenon gas. It doesn't matter. The relationship between the volume and the number of moles is the same. A 1 mole sample of nitrogen has the same volume as a 1 mole sample of xenon. And you can see that because the slope of the line is the same. They have exactly the same proportionality. And even though xenon is a lot bigger, the volume of the gas is the same. As the amount of gas increases, the volume of the gas increases. And in MindTap, you'll see that that is not the case when you're comparing mass. So it only works for moles. It only works for a number amount because the mass is going to have a different number of moles for each thing because each thing has a different atomic mass. All right, so our final example, we're going to calculate a volume based on a V1 and N1. So let's see, we have a sample of gas that contains 0.18 moles. So N1 is 0.180 moles. And that is nitrogen gas. It doesn't matter what kind of gas. And it contains 0.360 moles. All right, so actually, N1 is made up of 2 different gases, so we have to add those together. So in total, N1 is 0.540 moles of gas. Doesn't matter what the gas is, we're just going to add them all up. And this gas occupies a volume of 20.6 liters. So V1 is 20.6 liters. The following reaction takes place, and we're going to assume the volume of the sample after the reaction takes place. We're going to calculate the volume after the reaction takes place, and we're going to assume temperature and pressure are constant. So this one is kind of tricky. So this is a lot harder than the previous examples because this one is actually going to involve stoichiometry. So they gave us a number of moles of each of our things, each of our species. So we have to find out which one is the limiting reactant. So we have 0.180 moles of nitrogen gas. And for every mole of nitrogen gas, there is 1 mole of product because they don't have coefficients, so they are 1-to-1. All right, so 1 mole of nitrogen gas is 1 mole of our product. So that produces, so if we use all of the nitrogen gas, we produce 0.180 moles of product. And let's see if that's the same for hydrogen. So we have 0.360 moles of hydrogen. I'm going to write down here now. And our mole ratio is going to be 2 moles of hydrogen for 1 mole of product. So we actually see that we're going to end up with the same number of moles of product. So we're actually going to use up all of our reactants equally. So neither one is a limiting reactant. And we're going to make 0.18 moles of our product. And there's only one product, so that is all of the moles of gas on the other side of our reaction. So that is going to be our N2. So N2 is 0.180 moles of our product gas. So now we have N1, V1, and N2. So now we can calculate V2. So I'm going to erase. So remember, N1 was the sum of the gases, the sum of our reactants. So it was 0.54 moles. All right. So N1 equals 0.540 moles. V1 is our 20.6 liters. And we calculated N2 from our stoichiometry problem to be 0.180 moles. So V2 is our X. So V1 over N1 equals V2 over N2. So we're going to have 20.6 liters divided by 0.540 moles equal to X over 0.180 moles. All right, so we're going to get X by itself, so we're going to multiply both sides by our 0.180 moles. And we're going to find that X is equal to, let me just do this multiplication real quick. So 20.6 liters times 0.18 moles divided by our 0.54 moles. So X is going to be equal to 6.87 liters. Let's think about if that makes sense. So we decreased our moles of gas from 0.54 to 0.18 moles. So because they are directly related, we also decreased our volume. So that's how we do that. All right, that's it for today, guys. See you in class. So we know our ABC laws, as I'm going to call them. So A for Avogadro, B for Boyle, and C for Charles. So our ABC laws, we can use them to calculate changes in of the gases. So N, the number of moles, T, the temperature, P, the pressure, and V, the volume of the gas. If we're given the initial states of all the variables and the final states of the other three, we can use these relationships to calculate the change in the missing variable. So here is our Avogadro's law, here is our Boyle's law, here is our Charles' law. We see that V over N is equal to a constant, and P times V is equal to a constant, and V over T is equal to a constant. So if we multiply all those things together, we will see that those constants multiply into another constant, and P times V over N and T is equal to that new constant. Which means, like we saw for each of our ABC laws, we saw that, for example, for Boyle's law, we saw that P1 V1 equaled P V2. So now we're going to do something similar with all of our variables, and we're going to see that P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. This is what we call the combined gas law. The combined gas law is usually used to calculate the new pressure, volume, or temperature of a gas when some of these properties change. Very rarely will you also use it to calculate a change in the number of moles. That but it could happen. So that's why we say usually pressure, volume, or temperature. All right, so let's try using our combined gas law. We have a 7.15 liter sample of a gas. So that's a volume. I'm going to call that V1. 7.15 liters. Has a pressure of 1.23 atmospheres. I'm going to call that P1. We're still talking about the same gas at the same state. All right, and a temperature of 88 degrees Celsius. All right, that sample is allowed to expand to a volume of 8.46 liters. All right, we got our new volume, so that's going to be V2, 8.46 liters, and we got our new temperature. It was cooled to 30 degrees Celsius, so that's going to be T2. And we want to calculate the new pressure, so P2 is going to be Rx. So what about N? We usually see N, right? In this case, during the experiment. So I'll show you why we don't need to worry about N. All right, so I'm going to rewrite this in terms of our combined gas law. All right, so we have P1 V1 equals N1 T1 equal to P2, V2 over N2 T2. So because no gas escaped during the experiment, that means our number of moles did not change. We didn't lose any. So N1 is equal to N2. All right, so we want to solve this for P2. So I'm going to multiply N2 T2 to the other side. And then we're going to have P1 V1 N2 T2 over N1 T1 equal to P2 V2. So last step is to divide by V2. So that means V2 is going to be on the bottom of our set of variables. So we can see here that P1 times V1 times N2 times T2 divided by V2 divided by N1 divided by T1 is going to be equal to our second pressure that we're looking for. But because N1 and N2 are equal to each other, they cancel each other out. One's on top, one's on the bottom. So that's why we don't need to worry about the number of moles. So we have P1 V1 T2 over equal to our P1. So we plug everything in. So we have 1.23 atmospheres. We have 7.15 liters. And we have T2, which is our 30 degrees Celsius, which we need to be in Kelvin. So that is going to be 303. So 30 plus 273 is 303 Kelvin. All right, and down at the bottom, we're going to have our new volume, 8.46 liters, and our original temperature, 88 degrees Celsius, which is 361 Kelvin. You can check on your calculator, make sure I got that right. 88 plus 273 is 361 Kelvin. All right, so our liters are going to cancel out, Kelvin's going to cancel out, and we're going to end up with atmospheres, which is what we want. And our final pressure our pressure of the new state of the system is going to be 0.873 atmospheres. And we should always check to see if that makes sense. So our sample expanded. So we have a higher volume, and pressure and volume are inversely related. So a higher volume means a lower pressure. So yes, that the